Technology continues to shape nearly every aspect of modern life. From smartphones and laptops to electric vehicles and renewable energy systems, electronic devices have become essential tools in the way we communicate, work, travel, and innovate. But as technology advances, another challenge continues to grow at an alarming pace. Electronic waste, commonly known as e-waste, is rapidly increasing across the globe. Hidden within these discarded devices are valuable rare elements that help power modern innovation. Materials such as neodymium, dysprosium, europium, and tantalum are critical for manufacturing advanced electronics and clean technologies. However, recovering these valuable resources is far more difficult than many people realize. The process comes with major technical, environmental, economic, and logistical challenges that must be overcome before rare element recovery can truly reach its full potential. Welcome to Challenges in Extracting Rare Elements from E-Waste. As our dependence on technology continues to grow, so does the volume of electronic waste. Every year, millions of electronic devices reach the end of their useful life. Old smartphones are replaced, computers become outdated, televisions, household electronics, batteries, and countless other devices are discarded. Unfortunately, many of these products end up improperly disposed of, contributing to one of the fastest-growing waste streams in the world. But e-waste is not simply garbage. Inside many discarded devices are valuable materials that still hold tremendous economic and technological value. Rare elements such as neodymium, dysprosium, europium, and tantalum play essential roles in manufacturing modern electronics. These materials are used in magnets, batteries, displays, semiconductors, and energy-efficient technologies. Without them, many of the technologies we rely on every day would not function as effectively, or in some cases at all. Recovering these materials helps reduce waste, conserve resources, and lessen dependence on environmentally damaging mining practices. In many ways, e-waste represents not only a challenge, but also an opportunity. One of the biggest obstacles to rare element recovery is the incredible complexity of electronic devices themselves. Unlike traditional mining operations, where materials may be extracted from concentrated mineral deposits, rare elements inside electronics are scattered across numerous tiny components. For example, a single smartphone may contain more than 60 different elements. These materials are packed into incredibly small spaces, layered together inside circuits, microchips, speakers, magnets, displays, and batteries. Rare earth elements are often blended with other metals or incorporated into highly specialized components. This makes identification and separation extremely difficult. Traditional recycling systems are often designed to recover larger, more abundant materials such as aluminum, copper, and steel. Unfortunately, those methods may fail to effectively isolate tiny quantities of rare elements. In many cases, valuable materials are unintentionally lost during standard processing methods. This highlights the need for more advanced and specialized recovery systems. Separating rare elements from e-waste is far more complicated than simply dismantling a device. These materials are often deeply embedded within electronic assemblies and bonded to other materials in ways that make extraction extremely difficult. In many devices, rare elements exist only in tiny concentrations. Recovering them requires highly specialized methods that can isolate valuable materials without damaging or contaminating them. Traditional shredding systems often break components apart too aggressively, making recovery even harder. Once materials become mixed together, separating them can become expensive and inefficient. To address this challenge, advanced extraction techniques are being explored. Methods such as chemical leaching, hydrometallurgy, and pyrometallurgy show promise in recovering rare elements more effectively. However, these processes are often energy-intensive, expensive, and still evolving. Scalable and affordable solutions remain one of the industry's biggest goals. Recovering rare elements offers important environmental benefits, but if handled improperly, the recovery process itself can create risks. Many extraction techniques involve hazardous chemicals, including strong acids and industrial solvents. These substances help separate rare materials from complex electronic components. However, if chemicals are not carefully managed, they can contaminate soil, water systems, and surrounding environments. Poor handling practices may also contribute to air pollution and hazardous waste generation. Worker safety is another major concern. In some regions, informal recycling operations lack proper equipment, training, or safety standards. Workers may be exposed to toxic fumes, harmful dust, and dangerous working environments. These unsafe practices can lead to serious, long-term health consequences. That is why responsible recovery requires modern facilities, trained professionals, and strict environmental safeguards. Safe handling procedures are essential for protecting both people and the environment. Although rare element recovery holds tremendous promise, financial barriers remain a major challenge. Developing advanced recovery facilities requires significant investment. Specialized equipment, chemical processing systems, environmental controls, and trained personnel all contribute to operational costs. Managing hazardous materials safely also increases expenses. Another challenge lies in the fact that rare elements often exist in very small quantities. Unlike larger metals such as copper or aluminum, which may be recovered in greater volumes, rare materials can be difficult to extract profitably. Sometimes the cost of recovery exceeds the market value of the materials themselves. Adding to the uncertainty is the volatility of global rare element markets. Prices can fluctuate dramatically due to geopolitical tensions, supply chain disruptions, and global demand shifts. This unpredictability can discourage companies from making long-term investments. Without stronger incentives and policy support, many organizations hesitate to enter this emerging field. Technology has advanced significantly, but rare element recovery systems still face major limitations. Unlike recycling methods for precious metals such as gold and silver, there is currently no universal standard for efficiently recovering rare elements from e-waste. Many recovery systems are still in the early stages of development. Automation remains one of the largest challenges. Most recycling facilities are optimized for bulk material processing rather than precise material recovery. Machines may process large quantities quickly, but they often struggle to isolate delicate components containing rare elements. As a result, much of the sorting and disassembly process still relies heavily on manual labor. Workers often dismantle products by hand to isolate valuable materials. While effective in some situations, manual disassembly can be time-consuming, expensive, and difficult to scale. Researchers continue working on smarter automation systems that could dramatically improve speed, accuracy, and recovery efficiency. The future of rare element extraction may depend heavily on innovation. Another major obstacle lies in the uneven development of recycling systems worldwide. In many countries, specialized facilities for recovering rare elements simply do not exist. Even in regions with strong recycling programs, collection systems are often inconsistent. Many consumers remain unaware of proper disposal methods for electronics. As a result, valuable devices containing recoverable materials frequently end up in landfills or storage instead of entering recovery streams. Policy gaps also create challenges. Regulations governing e-waste vary widely between countries and regions. Without clear standards and enforcement, valuable materials may be exported, improperly processed, or permanently lost. Building stronger infrastructure is essential. Improved collection systems, public education, and investment in specialized facilities can significantly improve recovery outcomes. Stronger systems today will support better sustainability tomorrow. Solving these challenges will require collaboration across industries, governments, and research institutions. No single organization can solve the rare element recovery challenge alone. One important strategy is extended producer responsibility, often called EPR. This approach encourages manufacturers to take greater responsibility for products at the end of their life cycle. Companies can help improve collection systems, support recycling programs, and design products with easier recovery in mind. government support also plays an important role. Investments in research, grants, and recovery infrastructure can accelerate innovation and improve scalability. International cooperation is equally important. Electronic waste frequently crosses borders, making consistent global standards increasingly necessary. Working together helps create stronger, safer, and more efficient recovery systems. Partnerships between governments, recyclers, manufacturers, and researchers will be critical to long-term success. Despite the many challenges, the future of rare element recovery remains incredibly promising. Discarded electronics contain enormous untapped potential. Rather than viewing e-waste as a growing problem alone, society can begin treating it as a valuable resource. Recovering rare elements helps reduce environmental damage caused by traditional mining while supporting a more circular economy. Innovation will continue shaping the future. Improved automation, smarter sorting systems, advanced chemical recovery methods, and stronger infrastructure may dramatically improve efficiency in the years ahead. Responsible recycling practices also remain essential. Partnering with licensed recyclers helps ensure electronics are handled responsibly and valuable materials are recovered safely whenever possible. The future of sustainability depends on action. Governments, manufacturers, recyclers, and consumers all play important roles in building stronger recovery systems. The work happening today will help protect tomorrow's resources. Thank you for taking the time to learn about the challenges involved in extracting rare elements from e-waste and why responsible recovery matters. At Battery Recycling Solutions, we believe sustainability begins with responsible action and smarter resource recovery. Together, we can help reduce waste, recover valuable materials, and support a cleaner, more sustainable future. Reach us by phone, email, or visit our website to learn more about responsible battery recycling and recovery solutions. Recovering valuable materials from today's e-waste helps power a cleaner, smarter, and more sustainable tomorrow.